By late 1960, North American Aviation's X-15 had gone higher and faster than any aircraft had flown before, thrusting man and machine into the unknown. On August 4, 1960, test pilot Joe Walker took the X-15 well beyond 3 times the speed of sound, making him the fastest man alive. 8 days later, Air Force Captain Bob White climbed to new heights, taking the X-15 over 136,000 feet. This was just the beginning of an incredible program that would take man to extremes. By this time, a new generation of test pilot had emerged, men with dreams of going into space. Before reaching such ambitious goals, these men would need to train tirelessly in simulated cockpits. Here, NASA pilot Milt Thompson is becoming acquainted with the complex array of systems he would later validate in flight. The simulator was a relatively new training tool, which would become vital in preparing this new generation of pilots for future flights. Revolutionary pressure suits monitored the effects of weightlessness and extraordinary G-forces. However, these suits clearly provided little in the way of pilot comfort.
It was kind of like a sausage skin, and the more you blew it up, why, the more trouble you had bending your elbows and your knees, and the workload got very high then in what we called a hard or a pressurized suit.
This modified F-104 would become a kind of flying simulator, because its landing characteristics were similar to the X-15's. The F-104 would trace the X-15's flight corridor, following a series of tracking stations along the mountains of Utah and Nevada. By late 1961, all 3 X-15s were finally together at Edwards in flying condition. NASA's request for 3 X-15s had been fulfilled, and from now on, these aircraft would take turns breaking new records in both speed and altitude. The 3rd X-15, refurbished after an on-ground explosion, was now the most advanced of the 3. Equipped with a control system that could adapt to changing atmospheric density. The X-15 was refueled slowly overnight before a mission to avoid thermal shock to the airframe from the super-cold liquid oxygen propellant. Test pilot Bill Dana was aware of the volatility of the propellants used in the X-15. Their presence made sitting in the cockpit like sitting on a 17,000-pound bomb, but this didn't seem to bother Dana.
Gasoline's very explosive too, but we all drive automobiles that use it. And the same was true of the ammonia and the liquid oxygen, that under the proper circumstances they could have been explosive, but I never considered it a dangerous airplane at all. Quite the other. I was quite confident that the X-15 would get me home.
The X-15 would get Bill Dana home, but not before giving him the ride of his life. This white rectangle on the X-15's underside is frost caused by the liquid oxygen tank within the fuselage. All 9 tons of LOX and ammonia would be swallowed up by the powerful XLR-99 rocket engine in less than 2 minutes after ignition. This short period of thrust would be enough to leave the chase planes far behind in the quest to Mach 6. Despite all the simulator training, there was no substitute for the real thing.
It went from Mach 1 to Mach 6 in about 85 seconds, and it went from Mach 5 to Mach 6 in about 8 seconds. So it was, you knew you were hauling the freight when you flew the X-15.
Because of the excessive G-forces encountered, certain cockpit controls were modified because they were difficult to reach during the massive acceleration.
it was a tremendous physical effort to reach your hand out and grab the throttle to shut the engine down. That was a strong physical effort. You were just pinned back in the seat, basically, is what it was, and everything required 3 times as much effort as it would have under 1G.
Bill Dana would go on to fly 15 successful flights, including one on August 21, 1968, for which he was awarded astronaut wings. Later missions carried out further exo-atmospheric research, like the effects of micrometeorites on aircraft, as well as high-altitude photography, crucial data in paving the way for future space exploration. Dreams of creating an orbital vehicle that combined great speed and altitude with the landing capability of the X-15 resulted in the X-20. In many ways, the X-20's origins can be traced to the German engineers Eugene Senger and Irene Brett, who in the 1930s believed that a manned aircraft could skip on top of the atmosphere. Like the Mercury capsule, the X-20 was to be thrust into space aboard a series of ballistic booster rockets that would fall away as fuel was used up. The X-20 would finally enter orbit, but on re-entry it became very different from the Mercury system. Unlike the Mercury capsule, which would glide earthward on a very steep angle and under minimal control, the X-20 with its delta wing configuration would make a fully controlled glide at a very shallow angle. Despite the shallow descent of the X-20, re-entry would heat parts of the airframe up to 4,000 degrees Fahrenheit. To counter this, engineers investigated new exotic alloys, ceramic components, and a cooling water wall between the inner and outer skin of the fuselage. Despite the X-20's potential, political bickering and budget constraints resulted in cancellation of the project before it could get off the ground. At the same time, the X-15 program was going strong and pilots were going higher than ever. However, this simulator training failed to prepare them for the flying conditions of space, where conventional aerodynamic control was lost. Other means of control needed to be learned. This is the Iron Cross simulator, utilizing hydrogen peroxide thrusters to control movement. Attaching small thrusters like this to the aircraft provided a reaction system that could help control a plane at very high altitude, where normal aerodynamic forces weren't present. This concept was first tested in the X-1B. The NF-104, a rocket-boosted jet-powered aircraft, also successfully tested the reaction control system. The hydrogen peroxide thrusters were mounted on the wingtips and nose. These thrusters would prove invaluable as pilots pushed the X-15 to the edges of space. Time had come to break through the threshold into space. Bob White was chosen to make the attempt. On July 17, 1962, Bob White pulled away from the Earth at a 41-degree climb angle towards the stars. He quickly passed Joe Walker's previous altitude record, and before he knew it, had peaked at 314,000 feet, an astronomical 59.6 miles above the Earth. When White saw the entire western seaboard clear to Mexico, he knew he was in space. The third X-15, with all of its elaborate control systems uniquely designed for high-altitude flight, had clearly proved its worth, making it the highest aircraft ever flown. Bob White was the first to take a winged aircraft into space and return it safely to Earth. The following day at a White House ceremony, President John F. Kennedy awarded Bob White, Scott Crossfield, Joe Walker, and Navy Commander Forrest Peterson the Collier Trophy, aviation's highest honor. Air Force rules state that any military pilot flying over 50 miles high was considered an astronaut. White had exceeded this threshold and was awarded astronaut wings by General Curtis LeMay. Many pilots would now have the unique opportunity to experience spaceflight. Bill Dana was one of them.
The sky is absolutely black, just totally black, and then the horizon appears as a ring of bright blue just around the surface of the Earth. And it's not disorienting at all to be up at the altitudes I was at. I knew where the Earth was and what level flight was. I didn't have any trouble controlling my airplane. I was usually busy when I was up there, so I never had much time to sightsee, but I do remember one flight I went to 300,000 feet, and just over the top I took the time to look out, and I looked out and could see the Pacific Ocean to my right and the Gulf of California straight ahead of me. And that was an awesome sight.
This was not enough for Joe Walker, now embarking on his last mission. On August 22, 1963, Walker rocketed away from the launch plane, minutes later reaching over 354,000 feet, the highest the X-15 would ever go. After the Soviets launched Yuri Gagarin into orbit, U.S. policy shifted toward ballistic research, using rockets capable of sending man into space with relative ease. While the Apollo and Mercury programs flourished, the X-20 program fell victim to this shift. Now, orbiting men in capsules rather than winged aircraft became a priority.
Roger, you got the focus.
Meanwhile, the X-15 program was having its own problems. On November 9, 1962, test pilot Jack McKay was forced to make an emergency landing after an engine malfunction. During touchdown, the left landing gear fractured. McKay survived, but sustained serious injury. Ironically, this accident would result in the construction of the fastest airplane ever. In just over a year, the X15 #2 transformed into the X15 A2. External fuel tanks would provide the extra fuel to give additional thrust. It was now an aircraft capable of taking its pilot to new extremes. Creating an aircraft capable of going 8 times the speed of sound almost proved easier than protecting it from the blistering heat encountered at such speeds. Heat friction was particularly destructive to the leading edges of the wing and tail surfaces. Coatings of paint were used on wind tunnel models to expose these potential hotspots. It was decided that before each mission, the aircraft would be covered with a resin-based coating that would boil off at high speeds, taking the heat with it. Air Force Captain William Pete Knight was chosen to push the X-15 to its absolute speed limit. Knight had been slated for spaceflight in the X-20, but after program cancellation, he joined the X-15 program, replacing Major Robert Rushworth. The A2 had another unique feature. Because the ablative coating chars off at extreme speeds, the left windshield would need to remain covered to protect it from being coated with the residue. When the worst was over, the eyelid was opened, and the pilot would have a clear windshield to look through as he made his final approach and landing. After several familiarization flights, Pete Knight was ready to take the A2 to new extremes. The A2 was also equipped with a mock-up scramjet mounted on the ventral fin stop. NASA was interested in testing scramjet propulsion systems which depend on hypersonic velocities to achieve combustion. After the drop, Knight ignited the powerful XLR-99 engine and pointed the nose upwards. With the external fuel tanks and ablative coating, the X-15 was finally an aircraft that could keep up with its huge engine. In just over a minute, the external tanks were jettisoned as the aircraft pushed to its maximum speed. Prior to landing, the dummy scramjet needed to be jettisoned as well. Pete Knight had reached the blistering speed of Mach 6.7, over 4,500 miles per hour, making the X-15 the fastest winged aircraft ever. The A2 had finally validated the intentions of its original designers. Pete Knight was now the fastest man alive, but the aircraft had paid the price. The heat stresses were far worse than predicted. Even with the protective coating, the airframe was severely damaged. The scramjet mount had burnt through and fallen away.
On the flight to Mach 6.7, why the wake of the dummy ramjet, the Mach waves coming off the dummy ramjet impinged on the ventral fin and cut holes in both sides of it and did damage to substructures and subsystems inside the ventral fin.
Pete Knight had been unaware of the devastating extent of the aircraft's damage. The ablative coating on the leading edges had charred through, causing serious structural problems. Furthermore, Mach 6.7 was not even close to the speed that NASA needed to carry out research on the scramjet system. And there was no money in the budget to repair and modify the crippled aircraft. The A2 was the first X-15 retired from the program. Just over a month later, on November 15, 1967, X-15 number 3 would be completely lost. This tragic mission began without a problem. Air Force pilot Michael Adams took the aircraft over Mach 5. Then something went terribly wrong. Adams had somehow gotten off course, and on re-entry found himself in a spin. At 5 times the speed of sound, this was too much for the airframe, which disintegrated. Michael Adams did not survive. This cockpit footage provides an eerie reminder of the dangers of experimental flight. The only X-15 left was X-15 number 1, the first of the 3 to be built. This aircraft would fly 8 more missions, but never again to the extremes of speed and altitude that were accomplished by its 2 counterparts. The X-15's final missions further examined the obstacles of spaceflight. However, by the late 60s, landing man on the moon became a national priority, and interest in the X-15 program began to wane. When Bill Dana touched down on October 24, 1968, completing the 199th mission, no one realized that this was the last X-15 flight. It was intended the program would finish by year's end with the 200th flight. 10 unsuccessful launch attempts later, the program was canceled. Relics of history, the 2 surviving X-15s now sit silently as museum pieces, much of their data remaining on the shelf while man tried to reach the moon. There remains speculation as to whether advancements like the space shuttle would have come earlier had we taken up the X-15's legacy sooner. The X-15's first pilot, Scott Crossfield.
We've milked that database dry. We've used it all, and we're really out of it now. But no, the X-15, as far as useful information for the progress of aeronautics in space, is one of the most productive programs we ever had.
The X-15 bequeathed a truly great legacy, taking men to the extremes and beyond.
The X-15, designed to be purely and simply a research vehicle to provide aerodynamic, flight dynamic, and structural response data for use in the development of future manned hypersonic vehicles such as the Space Shuttle. No hypersonic wind tunnels, past or present, can provide accurate data for the design of a full-scale hypersonic airplane. The frontiers of flight today are the same as they were in the 1950s, the exploration of hypersonic flight. The X-15 will ultimately be viewed as the Wright Flyer of hypersonic airplanes. The X-15 flew to speeds and altitudes never previously achieved by winged vehicles. On the crisp, clear morning of November 9, 1961, a prospector working any of the many small mining claims in the bleak country around Mott Lake would have noticed a telltale broad white contrail signaling the approach of a strange formation of aircraft. If his eyesight was particularly acute, he might have discerned a giant Boeing NB-52B Stratofortress arrowing through Nevada's dark blue sky, flanked by two sleek little fighters, a North American F-100 Super Sabre and a Lockheed F-104 Starfighter. As he watched, he might have seen a long black dart drop from the B-52, followed by the sudden boom and crackling rumble of an igniting rocket engine. Boosted by 60,000 pounds of thrust, it let the head of the big bomber and its chase planes, accelerating upwards as it burned a ton of anhydrous ammonia and liquid oxygen every 12 seconds. It arced into the trans-atmosphere, its white exhaust trail pointing like a finger toward the future. Not quite 90 seconds later, it was level at 102,000 feet, streaking towards Edwards Air Force Base in Southern California at Mach 6.04. Air Force test pilot Major Robert White had just become the first man to take an airplane to Mach 6, 6 times the speed of sound, flying the second of 3 North American Aviation X15 research airplanes. Slightly less than 8 minutes and 200 miles later, trailed by another F-104 chase plane, the X-15, its propellants exhausted and now the world's fastest glider, dropped into a steep curve to a landing flare and touchdown on runway 18, marked out on the hard-baked clay of Rogers Dry Lake, the world's largest natural landing site. The X-15 program was a natural outgrowth of progression of aviation since the time of the Wrights. The biplane had given way to the streamlined monoplane, and by the late 1930s, the first experimental jet engines had appeared, promising an era of high-speed flight. But as an airplane flew closer to the speed of sound, it encountered compressibility, the bunching up of air around it as it neared Mach 1, causing high drag, buffeting, changes in structural loads, and even loss of control and in-flight breakups. For more than a decade, until Chuck Yeager flew the first Bell XS-1, later X-1, to Mach 1.06 in October of 1947, it seemed that the speed of sound might indeed be a barrier to the future flight. Afterward, aviation accelerated rapidly into the supersonic era. Mach 2 fell to Scott Crossfield and the second Douglas D-558-2 skyrocket in November 1953, and Mach 3 to Captain Milburn Apt and the first Bell X-2 in September 1956, though tragically, he perished when the plane went out of control during its return to Edwards. By the time of Apt's death, the X-15 program was well underway. Its designers faced formidable challenges. Bell had built advanced variants of the X-1 that could excel at Mach 2 and 90,000 feet, and the swept-wing X-2 could climb above 125,000 feet. Both hinted at control challenges the X-15 would face. In 1956, when test pilot Captain Ivan C. Kinch coasted to above 126,000 feet, his X-2 was like an artillery shell following a ballistic parabola. Near the top of its climb, as the plane decelerated after its rocket engine ran out of propellant, its ailerons, elevators, and rudder were useless due to the very low dynamic pressure encountered as it passed through the upper atmosphere. The X-2 began a slow left roll, arced over the top of its ballistic parabola, and, As its speed and consequently dynamic pressure increased in the lower atmosphere, its flight controls regained their effectiveness, and Kinchlow was able to guide it back to a safe landing on Edwards Broad lake bed. Clearly, flying above 100,000 feet, future rocket planes would require reaction controls, small jet thrusters such as those employed on the first manned spacecraft, in addition to conventional aerodynamic control surfaces. Aerodynamic heating and the high-altitude environment pose their own problems. Unlike supersonic flight, which is differentiated by the speed of sound and the distinctive crack of a sonic boom, hypersonic flight is characterized primarily by increasing aerodynamic heating with intensity hot airflows and sharply angled shock waves washing over the structure, their interactions producing even greater heat. The structure could not be conventional, for the plane would be subject to skin temperatures above 1,000 degrees Fahrenheit, necessitating extensive thermal protection. Inside the fully pressurized cockpit, the pilot would be more astronaut than airman, wearing a pressure suit and helmet capable of functioning in space-like conditions should cabin pressure be lost. Interest in hypersonic flight predated the supersonic revolution. The three great prophets of the space age, Russia's Konstantin Tsiolkovsky, the Romanian-German Hermann Oberth, and America's Robert Goddard, all advocated hypersonic airplanes as a means of flying into space, and German rocket enthusiast Max Valier, before his death and the explosion of an experimental rocket engine, recommended developing rocket-powered either planes as intercontinental airliners. In the 1930s, Austrian engineer Eugen Sanger and the mathematician Irene Brett undertook the world's first science-based hypersonic design, their so-called Silbervogel, Silver Bird. Proposed as a space transport and later as a global strike aircraft, it became an extraordinarily influential design study. Right after World War II, Joseph Stalin, according to a Soviet military defector, even sent a team into Western Europe on a fruitless mission to kidnap authors, hoping that Soviet Saga planes would make it easier for us to talk to the gentleman shopkeeper Harry Truman. The combination of the Saga-Brett study and example of the Nazi A4V2 ballistic missile greatly simulated post-war American, Soviet, and European interest in rockets, missiles, and hypersonic aircraft. While the Saga-Brett study had been purely theoretical, the A4 program had extensively studied Mach 4 plus wing derivatives, one of which, the A4B, flew before war's end, though it broke up during its terminal glide to Earth. The Soviet-American race to develop atomic-armed ballistic missiles fostered heating and re-entry studies, evolution of the blunt body re-entry shape, and high-temperature materials research. It also encouraged studies of rocket-boosted winged global-ranging hypersonic vehicles, even orbital spacecraft. In America, from all this sprang the X15 and X20 programs, though the latter never flew. The roots of the X15 reflected a broad base of military, industrial, and governmental research support. In 1951, Robert Woods, Bell Aircraft Corporation's chief engineer and a member of the National Advisory Committee for Aeronautics, prestigious aeronautics committee, called for development of new research airplane with performance similar to the A4's. His continued pressure led NACA's executive committee to endorse, a year later, investigating flight conditions between Mach 4 and Mach 10. The agency formed a hypersonic study committee under Langley Aeronautical Laboratory, now NASA Langley Research Center, engineer Clinton Brown, which subsequently advocated greatly expanded ground and flight research tests using models and specialized test techniques. The committee even suggested modifying the X2 with a strap-on booster to increase performance above Mach 4, adding reaction controls for flight safety. Program delays and eventual loss of both airplane doomed that idea. In 1953, the Air Force's Scientific Advisory Board concluded the time is ripe for a Mach 5.7 hypersonic vehicle, and the U.S. Navy's Office of Naval Research issued a study contract to Douglas for a Mach 7 plus design, tentatively designated the D558-3. Air Force and Navy interest proved crucial to getting the X-15 program off the drawing board and into the air. The next year, 1954, marked the genesis of the X-15. Another NACA study team, headed by John Becker, undertook preliminary design of a Mach 6 rocket-boosted hypersonic research airplane. It had a nickel alloy Inconel structure, rocket-like four-fin tail, and off-shelf rockets from the Hermes program. Becker's study anticipated many of the X-15's features and encouraged NACA that summer to invite the military services to join with it in developing such an aircraft. In October, they formed the NACA Air Force Navy Research Aircraft Committee, subsequently known as the X15 Committee. A joint program directive issued on December 23rd gave technical oversight to NACA and design and construction authority to the Air Force. The Navy and Air Force would jointly fund the effort. The Air Force supervised the design competition in 1955 between Bell, Douglas, North American, and Republic. Bell's Robert Woods, who had launched the company's earlier X1 effort, might reasonably have expected his firm to win, since it had already built and flown the X1, X2, and X5. Douglas's Ed Heinemann, with his D55 A2 Skystreak and Skyrocket, plus the D55-3 study, might have as well. Both companies produced relatively cheap designs, each promising to deliver 3 airplanes for a total cost of $36 million. Harrison's Stormy Storms, a veteran of North American's many fighter programs, led the design team that drafted his firm's entry at an estimated $56 million, the most expensive proposal. But both Bell and Douglas's designs were considered too technically risky, and Republic's, which was technically insufficient and also more costly than the Bell and Douglas proposals, came in last. Accordingly, despite the huge cost disparity, the Air Force notified North American on September 30th that it had won the competition. On June 11, 1956, after final negotiations, North American received a $42.9 million contract, about $349 million today, for the 3 X-15s. 3 months later, Reaction Motors Incorporated was awarded with a $10.7 million contract for their engines. The X-15 program involved far more than simply designing a new airplane, however novel it might be. Its rocket engine, pilot protection system, environmental controls and flight control system, as well as its flight test range, posed complex challenges. The X-15's XLR-99 engine, more than 3 times as powerful as the X2s and 8 times as powerful as the X1s, proved particularly risky. Developed by New Jersey-based Reaction Motors, the XLR-99 was based on the earlier XLR-30, used in the Navy's Viking high-altitude rocket program. Any hopes that the Viking experience would help with its design proved illusory. Unlike the XLR-30, which burned diluted alcohol and liquid oxygen, the 57,000-pound thrust XLR-99 burned 1,445 gallons of more explosive anhydrous ammonia and 1,000 gallons of iox. More significant, however, Talycol had to man-rate the engine, i.e., make it safe enough for operation in a piloted airplane, capable of repeated use, and both throttleable and restartable in flight. This was not easy to achieve, particularly as its high-speed turbopump, a potential source of disaster, fed the engine propellants at a rate of 167 pounds per second. Eventually, the XLR-99 became a reliable power plant with a rated operational life of about 1 hour, about 40 flights before requiring overhaul. Such reliability came at a price for a far longer than anticipated development period, compelling North American to complete the first 2 X-15s with older XLR-11 engines for their proving flights. The X-15 required a complex flight control system, a conventional fighter-like stick controlled an all-moving tail that furnished pitch and roll control, but was used only during approach and landing. During high-G acceleration, climb, and re-entry, the pilot relied on a side-stick controller, a reaction control system operating small hydrogen peroxide jet thrusters located in the nose and wings, furnished pitch, roll, and yaw inputs at high altitudes, where conventional controls were ineffective. Eventually, the third X-15s flew with an adaptive flight control system that automatically compensated for changing dynamic pressure, blending the reactor control system with the conventional aerodynamic controls. Since the X-15 was technically a boost glider, once it exhausted its propellants, the pilot had to carefully manage his energy to ensure he could reach Rogers Dry Lake. To help him in doing this, the X-15 would always be flown so that it had excess energy at burnout, which the pilot could use as bleed-off using large pedal-like speed brakes installed in the side of a massive dorsal and ventral fins. Unlike earlier rocket-powered aircraft that flew near Edwards AFB, the X-15 demanded a special flight test corridor, dubbed the High Range, running roughly 480 miles from Wendover, Utah, southwest to Edwards. Crossing multiple mountain ranges in the stark southwestern desert, the High Range was itself a notable technical accomplishment, foreshadowing the manned spacecraft tracking network NASA established for Project Mercury several years later. NASA furnished 2 tracking stations at Ely and Beatty, Nevada, as well as at Edwards. Furthermore, unlike research airplanes, the X-15 required a complex flight simulator to train pilots and undertake mission planning and rehearsal. The simulator was updated using data required during X-15 flights, with pilots typically spending 40 to 50 hours in it before undertaking the 10 to 12-minute flight. When the program commenced, it was hoped the X-15 might be flying by the end of 1957. Due to the complexity of its design and technical challenges involved, however, test flights did not begin until 1959. In the interim, NASA and the Air Force supported the X-15 development effort with extensive wind tunnel and free-flight ballistic tunnel testing, evaluated reaction controls on ground simulator rigs and on modified research airplanes including the Bell X-1B and F-104, and undertook extensive simulation studies to prepare for the crucial challenges faced by a hypersonic rocket plane having, for its first time, the lowest lift-to-drag ratio ever flown on a piloted aircraft. In October 1957, Sputnik had seized the public imagination, and the national debate over American science and technology that followed, NACA had given way to the space-focused NASA. Now the X-15 took on greater urgency and visibility as a symbol of America's progression into space. Vice President Richard Nixon presided over its rollout at North American's Los Angeles facility on October 15, 1958, a year after the Soviet satellite ushered in the new space age. It was a remarkable-looking aircraft, burnished metallic black, with thin wings and horizontal tail surfaces, and, because of the directional stability requirements of high supersonic and hypersonic flight, large meat cleaver dorsal and ventral vertical fins, the lower half of the ventral surface jettisonable during landing approach so that the X-15's landing skids could be a reasonable size. Although planners had originally thought the X-15 would use a modified Convair B-36 as a mothership, the retirement of the B-36 and the availability of the more powerful and capable B-52A led to its substitution for Convair's giant intercontinental bomber. Early tests with the X-15 proved far from encouraging. Piloted by North American test pilot Scott Crossfield, who had been so dedicated to the project that, as it began, he left NACA for North American, the first X-15 AF-56-6670 made its maiden captive flight on March 10, 1959, followed by its first glide flight on June 8. During the landing approach, Crossfield encountered serious longitudinal control problems that pushed his piloting skills to the limit, necessitating adjustments to the boosted flight control system. The second X-15 AF-56-6671 made the type's first powered flight on September 17. Propelled by 2 XLR-11 engines, it reached Mach 2.11 at 52,341 feet. He completed another powered flight into Mach 2.15 a month later, but then, on November 5th, disaster struck when an engine fire forced an emergency landing on Rosamond Dry Lake, during which 6,671 broke its back. While the second X-15 returned to North American for repairs and installation of its XLR-99, proving flights continued through 1960, with 670 still equipped with its interim XLR-11s. The third X-15, AF-56-6672, was the first completed with the big Tahical XLR-99. But during an Edwards ground test, the engine blew up, catapulting the rest of the airplane forward. Safe in its cockpit, Crossfield marveled at the X-15's strength and worried for the safety of crews trying to extricate him. The plane, like the second X-15, returned to North American for a rebuild. Not until November 15, 1960, 3 years late, would the X-15 fly with its XLR-99 engine, when Crossfield took 6671 to Mach 2.97, marking the end of its contractor flight test program. But now, the X-15 hits its stride. On March 7, 1961, Air Force Major Robert M. White became the first pilot to exceed Mach 4. He piloted the second X-15 across the hypersonic divide on June 23, attaining Mach 5.72. White completed a sonic trifecta by exceeding Mach 6 on November 9, as previously mentioned. Nor was the boyish airman the X-15's only record setter. On August 22, 1963, NASA research pilot Joseph Walker attained 354,200 feet in the third X-15, taking it into space. Marring this was a serious landing accident on November 9, 1962, that virtually destroyed the second X-15 and seriously injured NASA pilots Jack McKay. When an engine failure necessitated a heavyweight emergency landing on Mott Lake, 6671's skid landing gear collapsed. Even this setback was turned to advantage, for NASA lengthened the X-15 and added provisions for 2 huge drop takes and a dummy supersonic combustion ramjet engine installation on the shortened lower vertical fin. Eventually, on October 3, 1967, Major William J. Pete Knight reached Mach 6.7 flying this aircraft, designated the X15 A2. During the flight, unanticipated heating led to multiple structural failures, causing the scramjet module to separate from the aircraft and damaging the fuel jettison system. Knight, a superlative airman, landed safely. Sadly, shortly after Knight's remarkable flight, the fastest by a piloted airplane, the 20th century, Air Force test pilot Major Michael Adams, was killed in the third X-15. On November 15, 1967, during a high-altitude flight, it entered a Mach 5 plus spin, and it broke well above Mach 4 during an inverted dive into the lower atmosphere. The accident stemmed from a fatal combustion of instrumentation and control systems failures, plus human factors. Less than a year later, on October 24, 1968, the X-15 completed its last flight, its 199th, flown by NASA pilot William Dana. NASA attempted a 200th flight on December 20th, but Edward was untypically swathed in snow. Planners took it as an omen and simply retired the craft. The first X-15 went to the National Air and Space Museum, where it may be seen in the Milestones of Flight Gallery, and the second, the fastest airplane of the 20th century, to the National Museum of the U.S. Air Force. Altogether, 12 distinguished pilots, Scott Crossfield, Robert White, Forrest Peterston, Neil Armstrong, Joe Walker, Jack McKay, Milt Thompson, Robert Rushworth, Mike Adams, Bill Dana, Pete Knight, and Joe Engel had flown the X-15 to speeds and altitudes never previously achieved by winged vehicles. Its research program consisted of an aerodynamic and structural heating investigation phase from 1959 through 1963, and a follow-on program utilizing the X-15 to carry experiments into the upper atmosphere or to hypersonic speeds. Much of the applications program benefited from the contemporaneous Apollo effort, but it also helped sensor and missile detection efforts. X-15 flights produced more than 700 technical reports, establishing a database still considered essential today, as hypersonics advances into the second century of flight. The X-15 was by no means a perfect research vehicle. Under some circumstances, it had dangerous flight characteristics, and heavy impact loads sorely tested its landing skids. During re-entry, in-flight reconnaissance effects could interact with its flight control system. Early on, researchers discovered gaps in panels that permitted the entry of hot hypersonic air into its structure, necessitating fixes. Cockpit outer window panels shattered from heat-distorted panel frame structural loads, forcing redesign, and its nose landing gear twice extended in flight due to thermal stress. There were several landing incidents and accidents, one major ground explosion, and, of course, the sad loss of the third X-15 with Mike Adams. But overall, as a product of the pre-computer design era and without the benefit of modern tools such as computational fluid dynamics and computer-aided design and manufacturing, the X-15 constituted a remarkable achievement and an astonishing productive research program bridging the age of flight and the age of space. Fittingly, two of its most distinguished pilots went on to greater fame in the U.S. space program. Neil Armstrong became the first man to walk on the moon, and Joe Engle became one of NASA's first space shuttle mission commanders. Today, Air Force and NASA researchers pursue Mach 6 hypersonic flight with the air-breathing Boeing Pratt & Whitney Rocketdyne X15 A Wave Rider scramjet research vehicle. Tellingly, its designation, X51, was deliberately chosen and reserved to echo the X15 and remind researchers of the remarkable aircraft that, a half a century ago, did so much to make hypersonic flight a reality.
Here at Edwards Air Force Base, September 17, 1959 is a historic date. Early on this Thursday morning, the B-52 carrier takes the X-15 out for its maiden powered flight.
Hydraulic temperature's got -2, and holding since we passed the tower.
Test pilot Scott Crossfield is buckled in and ready for a ride to 40,000 feet, where he'll be cut loose for the first demonstration of this plane's abilities and performance. Flying chase will be Al White, North American's alternate, Joe Walker, NASA's chief test pilot, and the Air Force project pilot, Major Bob White. All vital observers today. They'll be at the controls of the X-15 in the near future. Ground crews climb in a variety of vehicles and stream out to wait for landing at the edge of the lake bed. Many eyes are on the dart-shaped plane this morning, but among the most important observers are the engineers at NASA. Using the ears of radio and the eyes of radar, they'll keep a close watch on the flight. FM signals transmitted will indicate the condition of each vital operating system. Each movement will be carefully plotted, carefully watched.
003, Edwards, cleared for takeoff.
Winds 220 degrees at 12 knots.
Prime responsibility for getting the X-15 to drop altitude rests on the aircraft commander, Captain Charles Bach, and the co-pilot, Captain Allaby.
Any tower, 003, rolling now.
As the bomber climbs out, the litany of checkout drones on. Item after item. Gauge, switch, and control are checked and rechecked. In the dim interior of the 52, Bill Berkowitz, launch monitor, has a close-up television view of system operation. The group has been this route before. 2 tries, 2 misses. The first try never left the ground. The second came agonizingly close, just 3 minutes from a drop, when a frozen valve canceled the effort. Delays are difficult to accept, but each time the system at fault was improved and a problem eliminated.
Figure's coming on now. Right. Power on now. Real slow to pick up hydraulic pressure.
Blake, how about it? It's a little slow, but it's up to speed now.
It dropped off in about 5 seconds, and it did go over 3,600. All flat, 510 on the tank.
3 minutes to drop.
Blankets level. Who wants that? What was the other thing? Okay, good check. Prime's going on now. Prime, watch out, but I can't see it. Yeah, I got, you got a blossom on the bottom one? They're both looking good. 30 seconds, give me a ready to launch right. It'll launch right on.
How about it, Blake? Think we're okay? Okay? All right, by me, let's go. Okay, Scott, let's give it a try.
Okay, you ready? I'm ready with you, everybody. Okay, here we go with the countdown. 3, 2, 1, release. Got 8 of them going. Roger. Heading uphill at 33,000 feet. Roger. It's going to cross the board. I'm on number 1 and climbing 235. Roger. Excellent, good, Scotty. Right on, you look really good. Okay, fine. Up on 50. Well, right.
The course for this flight is a giant rectangle around the lake, climbing to the north, then making a left turn to a westerly heading, and leveling off at 52,000 feet.
Take a little speed, but ease off. Right. Left turn. Right. I'm beginning to come around the final part of the turn. I dropped back in Mach number.
The record showed Mach 2.1, over twice the speed of sound, 1,385 miles an hour.
Burn out. Right.
On the first try, man and plane went 1/3 the way to the goal of 6 times the speed of sound. As the X-15 slows to subsonic speeds, the chase planes catch up and the glide portion of the flight begins. Now on a southerly heading, Crossfield begins his long glide to landing from 46,000 feet. Time in the air is precious, and the checkout continues all the way down.
Right. Roll forward. Steady side foot. You're very powerful. Ready. Got petrol? Okay, buddy, just a second. 8,000. I want to drop on the track. Here comes control now. You ready? Okay, parachute. You're fouled up. You're fouled up? No, the parachute, well, it's open. It's letting it down. How nice. 245? There you go. How do you cross it in it? Yeah, but yeah. 240. Okay, 240. Here, he's coming down tight to Ejection. Nice easy, Daddy. Goes on 210.
Maiden flight, a success. Today, flight research took another significant step forward here at Rogers Dry Lake. This lake bed has witnessed many significant events in the history of aviation. Born this day was a new tool for flight research, Using a new machine to probe into the unknown calls for caution, and weeks later the second flight showed that the performance could be repeated and excelled. Digesting the knowledge from these first tries, the program became more ambitious, and another step up the ladder was planned, one that would extend the operating area. Countdown for powered flight begins at midnight. The previous week has seen many test hurdles, each one met and overcome, each one establishing with greater authority the right of the X-15 to be in this fueling area. All the control points have been passed this far, and now the touchy, toxic, volatile propellants are added one by one. As tanks are gradually filled, crew members take long last looks into the vitals, then close the doors. Dawn finds the service carts being pulled away, with the two aircraft again standing ready. Even the most carefully controlled experiment has its element of risk, and the sober faces of every member of the team reflect their concern. Each research flight has fresh new goals. Each one is a cautious step forward into unexplored areas. The intention of this flight is to make a straight climb to 80,000 feet, hitting Mach 2 at the peak. The now routine checks of plane and engine pass uneventfully, and just past 9 in the morning, the third voyage of the X-15 begins. In a split second, the plan of exploration is abruptly changed to one of survival as the pilot peels out the plane for damage and heads for Rosamond, an emergency landing area. Never has the pilot been more vital. Now it's his responsibility to get the plane on the ground safely if he can. Trouble came in pairs on this day. The engine failure was complicated by a structural break, and both were at this time unexplained. The plane was on the ground, the pilot safe, but there were new problems. Investigators found that the rocket engine had suffered an ignition failure, leaving a chamber loaded with explosives. When this mixture finally ignited, the chamber ruptured. This explosion triggered another series of events leading to additional damage. Under normal conditions, the tanks are almost emptied, but jettison in a nose-down emergency glide leaves more propellants, more weight in the fuselage. Because of this increased weight, the nose of the plane had to be higher than usual during landing. Although the touchdown was smooth, the nose-up angle was beyond the design limits, and the break occurred when the nose wheel slammed to the ground. A day and a half after the accident saw the airframe in its original jigs at the factory. The damage that seemed crippling was quickly repaired, the broken halves rejoined. This old project is one set to gain knowledge, and even from failures, lessons are learned. The fuselage was strengthened and landing gear was redesigned to absorb more shock. Rocket engines were modified to increase reliability. 5 weeks after the unsuccessful try, the plane, now whole and improved, began its trek back to Edwards Air Force Base. Weeks have slipped by since the accident, but the time has been traded for knowledge. More is known now. Certain hazards have been ruled out. The machine is better, more able. This is the #1 plane of the series, modified, improved, and set to show its capabilities. It hangs frosted, smoking, ready.
Right here. And I'll look all the way to the door. I can make order, I can.
Pouring on the rocket power, the X-15 streaks to a new high of Mach 2.5. 1,660 miles an hour at 67,000 feet. January saw the #1 airplane make its final qualifying flight. Delivery to the Air Force and NASA started a new crew on acceptance check and pre-flight readying. Joe Walker, chief research pilot of the National Aeronautics and Space Administration, was the first to show that the X-15 is not a one-man airplane. At this time, 2 X-15s were flight ready. #1 was involved in the Air Force NASA program to take the airplane with its present engines and push it to the limit of its abilities. And Joe Walker's first flight denotes the start of this research phase. The #2 plane was still being flown by North American for investigation of stability, control, flying qualities.
Okay, that's nice. You'll turn a little to the right now. I would say that's okay. Okay, we got all 8 going now. Everything looks good. Okay, I need to recognize how far out I get now. Okay.
The drop was standard, the flight routine, the landing uneventful. 2 weeks later, another new face appeared. Major Bob White climbed the ladder to the cockpit to try his hand at rocket plane flying. An hour and a half later, the X-15 Pilots Club had another new member. The Air Force's project pilot had made his initial run and now was ready to start some serious research flying. The spring of the year saw a flurry of activity with 2 X-15s flying and North American racking up 9 drops with the #2 airplane. The Air Force and NASA alternated pilots on a separate series of 9 research expeditions, flights that kept inching up on the world speed and altitude records. Both company and governmental pilots kept investigating the flight abilities of the planes in different quarters, feeling out the new machines, steadily pushing the operating area out farther, gaining confidence. All flying during this period was done with the XLR-11, the small engine package. Its thrust of 16,000 pounds was adequate for early investigations, but everyone was waiting for the big engine. The XLR-99, a brute that would blast out nearly 60,000 pounds of thrust to drive the plane to peak speeds and altitudes. This engine is installed in the third and last plane of the series, which has always been slated to be the test bed for this new power plant. And Crossfield uses his time in between flights to ring out the installation. Preliminaries are out of the way, and this run will be one of the final before flight. This long-awaited engine can be throttled, having an idle output of 30,000 pounds, but able to be regulated between idle and 60,000 pounds of thrust. Today's runs are the climax of a long series of tests proving the installation. After this start, they're ready for flight.
Valve malfunction. Throttle off. Reset.
In a split second, years of planning, months of test and grinding work went up in smoke. There was only one real observer, one eyewitness, the pilot, Scott Crossfield. Scott, what was your immediate reaction?
Well, it was the biggest bang that I'd ever heard. Fortunately for me and the airplane, the explosion blew the forward section, the tanks, and the cockpit out of the blaze, or out of the major part of the blaze. And the firemen were right on their toes, and they moved in to blanket the tanks and the fire area with foam. The first reaction we had was that the engine had blown up, but like many first impressions, this was wrong. As soon as the parts cooled down, a disenchanted group of engineers moved in, and as you might imagine, things were pretty well scattered about. We also took a close look at the film that you've just seen, and here are a couple of frames that gave us our first clue. Just before the blow-up, a cloud of vapor appeared ahead of the engine. So the search was concentrated on this area. Following up this lead, we found that the hydrogen peroxide tank had been rammed, smashed open. But with what? Lining up with the tank is the center structure of the ammonia tank, and its shape matched the impacted area of the hydrogen peroxide sphere. But how could this part fail? Likely through overpressure. Now, a check of the instrumentation showed tank pressures far over normal. Again, the question, why? The pressure regulator was recovered and checked. It was determined that freezing caused by the very low temperature pressurizing gas had caused the regulator to stick full open. But there's a safety, a valve to relieve overpressure. This valve and the entire release system was also checked. Here it was determined that a flow-sensitive relief valve, combined with a vapor disposal equipment, had created enough back pressure to fail the tank. So, a frozen regulator, a Foley relief valve, and a high back pressure relief system had gotten together, and we had wrecked an airplane. The entire pressurizing and release systems were analyzed, redesigned, tested, and retested. We ran the combination time after time, deliberately creating the most severe failures possible. Weeks passed before we and everyone else were convinced that the problem was licked. As a measure of how the confidence was restored, here is what happened on the 4th of August.
On this historic date, Joe Walker let out a yip of joy. He had just pushed the modified small-engine airplane to a new speed record, then made his report to the public.
How does it feel to be the fastest living human? I don't know if I feel much different than I did yesterday, except that the waiting for the flight is over finally.
165.
Out of back area, Joe.
Roger.
Gyro look good. Go ahead.
Go.
Burn out. Plus 3 plus. You made it. At what point did you reach your maximum speed?
If you notice the vapor trail from the engine, at the instant it cut off, that was the point at which I reached the maximum speed.
Now, what was your altitude then?
Around 66,000.
How long were you going that 2,150 miles?
Just one instant.
Then, on the 12th of August, just 8 days later, Major Bob White was up before the cameras after his 136,500-foot record-breaking altitude flight.
The flight today offered, I would say, no problems and nothing that could be considered a limitation as far as man's ability to fly an aircraft.
Starting to pull up. Right on the track. Your angle looks good, Bob. You're going up. That's nice.
Once I pitched up and reached the highest climb angle, I was very definitely impressed that I was going, well, almost straight up. Of course, it wasn't straight up, but it appears to be that way from the cockpit.
That's coming up on 10 now. Okay. Angle's very good. Going through 11 now. Out now at coming 12 now. Got 12.6 and 13. Very sensitive. That's still good. Fantastic up here.
What you see at this altitude impressed me as being the most dramatic point of flying at over 130,000 feet. The very dark blue sky and the lighter band that was immediately surrounding the Earth, and then, of course, the many, many miles off in the distance that you're able to see. Looking to the future, I would say that we hope very much, and I would particularly like to continue on in work that would take us to higher altitudes with manned aircraft.
Now the full potential of the airplane with the small engines had been fully investigated. While the number 2 airplane was being fitted with the big engine, number 1 began a series of training flights. The full crew was now given a chance to try its hand at piloting the research plane. Commander Peterson, the Navy's representative, was the 4th man to ride the X-15. He made 2 flights in early fall. Then Jack McKay, NASA research pilot, took his first ride at the end of October. Captain Rushworth, the Air Force backup pilot, was next to show his skill at rocket plane flying. NASA pilot Neil Armstrong's last 2 flights closed the year. Training flights filled the gap while the number 2 was being given a complete checkout with the large engine. Since that ill-fated day in June when the explosion ripped the number 3 ship in half, maximum effort has been exerted toward getting another engine and installing it in Ship 2. Months of work, weeks of painstaking trials, round-the-clock days of final pre-flight were at last put to the test on the morning of November the 15th. This is the X15 in its final stage of development. This run, if successful, will mark the beginning of a whole new era of flight research.
Explosive. Okay, get out here, Scott. Okay to go? Right. Right there. 25. Don't bite it.
Auto cooling got down.
Got it? Launch.
Turning up to the right, Scotty.
The launch, the tank pressure is going up to 60. And I'm going up here. I'm reading 320. Launch tank is holding at about 55. About 1 and 2, that big one open. There's a lookout.
That's real good, Scotty. You made about a 10-degree turn to the right when you came off.
With the new engine loafing at idle, the plane could go to 4 times the speed of sound. so the speed brakes are open to stay close to Mach 2.
Scott, a little right course, you're okay.
There you go. George, could you tell us in your own words how the flight went, what you thought of it?
Very well, and the engine and its power is impressive.
What was your maximum altitude speed? Did you have a chance to check that yourself?
Yeah, I got about 80,000 feet and a Mach number approaching 3.
Scott, your radio talk sounded a bit hesitant this morning before takeoff. What was that about?
Oh, no, I think you misinterpreted that. Of course, we've been doing the best we can to get this flight off for 5 years. There's any hesitancy there.
Well, having observed the minimum thrust performance of the engine, do you think that the airplane now will be able to live up to its design promises of altitude and speed, or will it exceed it, or how do you feel?
Yeah, really, without question. I got a little faster today than we'd planned, and we have in our previous flights, in my flights, gotten faster than we planned, because for once in history, we've overestimated the drag on the airplane. I think it'll exceed its original expectations.
Just 7 days later, the second flight was launched, and on the 6th of December, the third. Both showed the engine to have all the abilities claimed of it. These two eminently successful flights closed the year. But the story of the X-15 stands not in the past, but in the future, when every flight is a record breaker, when every trip away from the B-52 is an unparalleled research mission. Human hands will be learning a new skill, to thrust deep into unexplored areas, capture vital information, then settle to a safe return from that twilight land standing between Earth and space.
Okay, your position looks good, Joe. Let's go Dallas Ion.
Haven't got the 1 minute warning yet. One minute. LSI. Push to 10. Right, Joey. Prime. Igniter ready light. Pre-cool on. Igniter right. 20 seconds to launch. Everything checks here.
Your position is good, Joe.
Pump idle. Right pump. Good igniter. Ready to launch now. Hot light. Okay.
This is the X-15 research aircraft, designed to investigate the problems of manned flight in a near-space environment. Altitudes up to 50 miles, speeds up to Mach 6. High-speed aerodynamics, aerodynamic heating, structural design, aircraft stability, and control in space and re-entry. This was the kind of information it was to provide, and provided it did. Here's the story. Before the X-15, the question had been, what is to be man's role in space travel? Can he pilot an aircraft out of the Earth's atmosphere, fly it in space, then re-enter the atmosphere and bring it back to a safe landing on Earth? There were many unknowns to be discovered, many problems to be overcome before the answer would be known. That today's test flight is almost routine is a tribute to the comprehensive program that has moved step by step to prove that man can pilot an aircraft into space and return.
Give us a 20,000-foot check, Joe.
Coming up on 20,000 now.
Okay, I know you've done it, but check your flaps and circuit breakers.
Roger. Done it.
Ready to go pressurized?
Pressurized.
You're in good shape.
Flaps. And flips are coming down. Here. Can't seem to get her on the ground. Real nice. Well, sir, now we're done with the second cross-country. Yeah, boy.
Real good flight, Joe. This is your happy controller going off the air.
There have been many men who have helped make the X-15 project a success. One of them is aircraft research engineer Hartley Soule, who was originally in charge of designing and building the X-15 aircraft.
Of course, I'm retired now, and the X-15, she's not the queen of the hangar anymore, although she's still hard at work. But I remember years ago, you know, it was long before Sputnik that we decided to build the X-15. This airplane, the first hypersonic aircraft, was going to be our first manned space probe. This was a logical step in the research aircraft program that had begun even before the end of World War II.
From the beginning, the research aircraft program was a cooperative affair. The National Advisory Committee for Aeronautics, predecessor to NASA, the aircraft industry, the Air Force, the Navy, working together. Their first effort was directed at breaking the sound barrier. And the aircraft that would do it was the X-1, designed to acquire flight data at the speed of sound. On October 14, 1947, with Air Force Captain Charles E. Yeager at the controls, the X-1 made the world's first supersonic flight. Other research aircraft soon followed the X-1. The Douglas D-558 Phase 1, to investigate flight with a straight wing at high subsonic speeds. The Northrop X-4, designed to fly without a tail. The Douglas D-558 Phase 2, to study flight characteristics of swept-wing aircraft at transonic and supersonic speeds. The Bell X-5, designed with variable sweep. And the Douglas X-3, to investigate thin, straight wings at speeds beyond Mach 1. The Bell X-1A, with its increased performance, first of a series of follow-on aircraft to the original X-1. The X-2, another Bell airplane designed to explore aircraft behavior at altitudes above 100,000 feet and Mach 3 speeds. The X-1E and X-1B, both later follow-ons to the X-1. Step by step, these different aircraft helped nibble away at the unknown, until by 1956, the frontiers of manned flight had been advanced from speeds of 500 miles an hour to Mach 3, and from altitudes of only 40,000 to more than 100,000 feet.
Speed, altitude, sure we kept going higher and faster than we'd ever been before. Only because that's where new information, where the unknown has always been found in flight, above and beyond the limits you've already reached.
As early as 1952, the X-15 aircraft was being conceived by the people at NACA. At the Langley Center in Virginia, they began investigating the unknowns associated with flight to the thinnest edges of the Earth's atmosphere. One unknown concerned aerodynamic heating. The X-15 would be the first aircraft to push from supersonic to hypersonic speeds, where the flow of air would heat the leading edges of the plane to 1,300 degrees Fahrenheit. Experiment after experiment was run to see if this extreme temperature would weaken or melt basic materials. The data resulting from tests run well beyond temperatures expected for the X-15 proved that there were materials that would withstand this kind of heat. Another problem, after rocket engines shut down, the X-15 would be thrust into a ballistic arc in air so thin that normal aerodynamic control would be impossible. How then could the pilot control the aircraft? The answer? Reaction controls that would allow him to correct roll movement and position the aircraft properly for re-entry through the atmosphere. But the designers knew the problems of control would never be fully solved until an X-15 aircraft was actually built.
We knew the X-15 would look something like this. We knew that it would be a manned aircraft that would fly more than 4,000 miles an hour and as high as 250,000 feet. We knew that, like the X-1, the X-15 would be air-launched and propelled in its flight by a rocket motor, the most powerful engine ever installed in an airplane. Of course, we didn't know what kind of a rocket motor that would prove to be.
There'd never been anything like it. Designed for a manned system, the 50,000 pounds of thrust in its single chamber had to be controllable at the pilot's discretion. He had to be able to throttle this engine in flight.
This is Harry Cook, program manager for the X-15 rocket engine.
The LR-99 rocket engine was designed and built for the X-15 by the Reaction Motors Division of the Thiokol Chemical Corporation. We had had some experience in this field. Reaction Motors had built power plants for all of the X-1s and for the D-558 Phase 2 aircraft. But those rocket engines we had made for earlier research planes were primitive forerunners of the engine we built for the X-15.
57,000 pounds of thrust with a throttle attached. No engine like this had ever existed before, but Thiokol built one for the X-15. Now, what kind of airframe could be designed to carry such an engine?
The X-15 was designed and built to take the stresses encountered at hypersonic speeds, to go to extreme high altitude and to beat the heat, survive the extreme high temperatures that build up on the wing, fuselage, and tail during the re-entry to the Earth's atmosphere. The engineering research contribution we made at North American Aviation to the X-15 project was to take NASA's proposal to build this aircraft and to find out how they could be met.
Harrison Storms. He was in charge of the X-15 program at North American Aviation.
For example, they proposed to use a new nickel alloy metal for the protective sheath or skin on all three of the airframes of the X-15. We had to find out how it could be used.
Inconel X was the name of the new nickel alloy. It was developed to withstand the searing temperatures at hypersonic speeds, temperatures of 1,200 degrees Fahrenheit or more. But to use Inconel X, it had to be cross-welded, and no one had been able to do it before. A major milestone was passed when North American discovered how it could be done. North American also originated the idea of fairings along each side of the X-15 fuselage to house control cables and hydraulic lines. This left the entire fuselage volume for power plant plumbing, as well as fuel and propellant tanks. Another invaluable North American contribution was the X-15 flight simulator, permitting pilots and ground controllers to plan and practice flights without ever leaving the ground. From an exact replica of the X-15 cockpit, the pilot could actuate hydraulic and control systems identical to those on the aircraft itself. All this was tied into an analog computer that could program actual X-15 missions and simulate every conceivable in-flight problem the pilot might expect to face. Practice in the flight simulator was just one phase of pre-flight preparation. Another took place in the centrifuge at the Navy's Air Development Test Center at Johnsville, Pennsylvania. There, pilots learned how to take the heavy G forces they would meet when they flew the X-15 up into space and back down again. Hours of training here, added to hours in the simulator, extended the pre-flight pilot training period into weeks and even months. Then came the dramatic moment. The X-15 and its B-52 launch aircraft were ready. North American test pilot Scott Crossfield was ready. Step by step, the X-15 research project had moved to this important event. Now, the first of 3 X-15s was about to begin a series of test flights. The schedule called for an orderly progression of tests. In the first flights, the X-15 would remain attached to the B-52. Then a glide flight would be tried. Only then would powered flight be attempted. This careful program of flight tests, flown by pilot Scott Crossfield, proved the X-15 would do just what its designers hoped she would.
From March 10th, 1959 until late in 1960, when we delivered the 3rd aircraft to the Air Force, I made 14 captive flights, 1 glide flight, and 10 powered flights. It was all pretty much routine. We, North American that is, went up there to check out the aircraft, to check out the systems, to see how she handled and whether or not she'd meet the specs before we turned her over to the Air Force. But you'll have to go up to NASA's Flight Research Center at Edwards to find out how the actual test programs worked.
Edwards Air Force Base in the Mojave Desert in California. This is where the X-15 story comes together. For here is where test flights of all high-speed research aircraft since the X-1 have taken place. Like all the programs conducted here, the X-15 Flight Research Project had a simple basis. A series of progressive steps to higher speeds and to higher altitudes. But each step, each flight itself, had a more immediate purpose than simply to gain more speed or altitude. And each flight was carefully planned to make the most effective use of this aircraft as a research vehicle or tool. Paul Bickle, director of NASA's Flight Research Center.
Each flight provided new information or confirmed wind tunnel or theoretical data on the characteristics of an airplane performing in a very advanced flight regime. Each flight grew out of one that had already taken place and led to another still to come. Of course, the X-15 flight program really began in the simulator months before the first airplane was delivered to us.
Joe Walker, Chief NASA Edwards research pilot, physicist, and pilot of a long list of research aircraft.
Practice or planning in the simulator is the beginning of every flight that's ever been made in the X-15. All pilots assigned to the project first become familiar with the handling characteristics and timing of the X-15 on any given mission in the flight simulator. It's been good insurance for all of us.
One of the X-15 pilots who has spent many hours in the flight simulator is NASA's Milton Thompson. Here, Thompson flies a practice mission under normal procedure, with pilot engineer John McKay working as his flight planner. In a nearby room where the analog computer is housed, the activity in the cockpit can be monitored on closed-circuit TV. The pilot's control movements and the airplane's simulated response are checked on a plotter by the flight planner, who will monitor the actual flight from the NASA Edwards Control Center on the ground. The pilot's inputs may also be monitored and recorded by other instruments. Variations from the planned mission are then simulated, so the pilot will learn to recognize their effects on the aircraft. For example, he may get a problem involving changes in stability. These changes are fed by the computer to his cockpit instruments. The pilot reads the changes and makes control inputs to bring the aircraft back to normal. His response is monitored and evaluated. The pilot also goes through what is called trouble school, where failure of one or more of the X-15's major systems is simulated. Again, his reaction is monitored. Each pilot gets further practice by making a number of flights in a modified F-104 aircraft. He flies over his upcoming X-15 flight course to establish geographic checkpoints and key altitudes in the landing pattern. All flights are made over the high range, a network of ground tracking stations stretching from Wendover, Utah, 485 miles south to Edwards in California. The range consists of a master station at Edwards and radar stations at Ely, Nevada, and at Beatty. The flight corridor is 50 miles wide, and it contains a number of dry lake beds where emergency landings can be made. Two kinds of powered flights are made over the high range. One, a ballistic type, high-altitude run up to and even above 250,000 feet. And two, a high-speed run made at a lower altitude, usually 60 to 70,000 feet. During his practice flights in the F-104, the pilot must also familiarize himself with the timing and positioning for an X-15 landing at both primary and alternate landing sites. And he makes practice landings, using predetermined settings that can simulate the low-lift drag ratio of the X-15. Nothing is left to chance, in the air or on the ground.
These precautions paid off during the following flight, when the pilot realized he could only get 30% power, and that consequently he would have to make an emergency landing at Mud Lake.
Ready to launch. 5, 4, 3, 2, 1.
That's a good light. That's a good light. Go on, try to give the chamber reading.
Got 12 degrees.
Okay. Chamber pressure.
Pressure to 50.
Push your throttle up and give us chamber pressure.
Oh, yeah, I have chamber pressure about 200.
Roger, you got the full throttle?
Up ramp.
You're running at 30%.
30%? How are we going, Bob?
Roger, you're going by Mud Lake. It looks like a landing at Mud Lake.
Right. Looks on the floor plan there, like there's a very tiny bit of wind from the south and a little bit east, so it's like...
Wrecked though it seemed to be, both the aircraft and the pilot survived to continue with the program. This was one of only 3 major accidents, all non-fatal, that have occurred in more than 120 flights with the X-15, a remarkable record of reliability. In February 1964, the plane that crashed on Mud Lake only a few months before came rolling out of the North American plant with a new designation, the X15 A2. This modified version was rebuilt for flight to Mach 8, 8 times the speed of sound, where the airflow temperature rises to 2,400 degrees Fahrenheit. The new X-15 had a new heat-resistant protective coating, a new inertial guidance system, a longer fuselage, external tanks to carry more fuel for longer flights, and lengthened landing gear. All the while this new X-15 was being built, tests were continuing with the other 2 aircraft, and they continue today. For every flight, the procedure is essentially the same. Every phase carefully planned, every second of actual flight time mapped out in advance. That way, Every man involved knows exactly what his job will be from the beginning to the end of the flight. Hours of preparation, weeks of planning, months of study, whole years of research. All this goes with the X-15 each time she leaves the hangar for another flight. For after all, no matter how many flights have been made before, each new test will probe a little deeper into the unknown. She is a research tool, this sleek black aircraft, carrying a host of instruments, gauges, and recorders to explore the unknown. And every second of her time in flight must be carefully charted. That's why at the Ely High Range Station, at Beatty, at Edwards, sensitive antenna watch and listen to each flight. That's why the pilot's heartbeat never really leaves the ground. And that's why in each control room on the ground, the plotting board is carefully watched for any unplanned deviation, for any unlooked-for change in the pilot's reactions or in the behavior of the aircraft. Position and velocity computers, telemetry receivers and monitors, data receiving and recording equipment, communications receivers and transmitters, they all go into action at the beginning of every flight. In NASA 1, the project men stand by, alert for any possible trouble in the flight, while flight surgeons prepare to watch the pilot's physiological response, his pulse, his body temperature, heart action, respiration rate. All of this will be telemetered to the ground. Then, as always, when time for takeoff draws near, attention focuses on the man chosen to fly the mission. Because of this, the X-15 pilot becomes, in effect, the symbol for the entire research team. The one man who represents all the others who have worked so long and so hard to make the project a success. And it is a proud record of accomplishment they've achieved. They have designed and built an aircraft that could be piloted into space and flown back safely to a controlled landing on Earth. They have accumulated important data on aerodynamic heating at hypersonic speeds. They've learned about stability and control of aircraft during flight in near space and re-entry to the Earth's atmosphere. And perhaps most important of all, they have dramatized the potential of piloted high-performance aircraft in a space environment at a time when much of the world's gaze was turned toward orbital flight. The X-15 research project has long since achieved its original goals. The aircraft has been flown successfully more than 120 times, and although setting new records wasn't its purpose, it has set a few along the way. Altitude, 67 miles. Speed, Mach 6, 4,104 miles an hour, the highest and fastest a winged aircraft has ever flown. Today, the X-15 moves on to further accomplishment. But now the Thoroughbred has become a workhorse, carrying a heavy payload of instruments, undertaking studies of the near-space environment possible before only with unmanned satellite and rocket-borne probes. There are many people who should share the credit for the continuing success of the X-15 research project. But perhaps they will understand if we seem to focus on those who have actually flown the many research aircraft since the X-1. By saluting these courageous men, we also pay homage to all the others who have helped us move step by step, deeper and deeper, into the unknown outskirts of space.
Yeah, Tone, we have an ejection. We have an ejection. The aircraft is descending over the North Base area. I have a chute. The pilot's out of the seat and the chute is good. Okay, Bravo, copy.
We had a highly competent team, very experienced, many flights under their belt. We had a number of pilots that flew the airplane. The pilot in particular that was flying that day had been on the program from the very beginning, highly experienced with the X-31.
Each mishap has its own set of circumstances and its own sequence of events. But you find similar issues: communications, complacency, assumptions that haven't been warranted, human frailties. And you have to account for these things in a program.
This is like a chain. You make a chain when you have any of these accidents, a chain of events. Any link of the chain, if it were broken, you would not have an accident.
This was the A-team. We had the best people from every discipline, from every organization, and we lost an airplane. So if it can happen to the best team, it can happen to any team.
The X-31 research effort began in the late 1980s as an international program involving DARPA, the U.S. Navy, Deutsche Aerospace, the German Federal Ministry of Defense, and Rockwell International. The program's goal was to explore the tactical utility of a thrust-vectored aircraft with advanced flight control systems.
The X-31 was a real pioneering program. And in fact, the X-31 program pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HARV.
The initial X-31 flight tests were conducted at Rockwell's facility in Palmdale, California. But in 1992, NASA and the U.S. Air Force joined the X-31 research team, and the test flight program was moved to the Dryden Flight Research Center on Edwards Air Force Base. And before too long, the X-31 was turning in some extremely impressive results. By any measure, the X-31 was a highly successful program. It regularly flew several flights a day, accumulating over 550 flights during the course of the program, with a superlative safety record. And yet, on the 19th of January 1995, on the very last scheduled flight of the X-31's ship number 1, disaster struck.
This particular flight had been on the books for some time to get done, and it was, by our standards, an absolutely routine flight.
We were not expanding the envelope. We were not trying anything new. We were flying a new pitot-static tube, but this was in a routine mission, a routine task, routine flight environment with an experienced pilot and experienced crew.
But while the flight was routine, there had been some changes to the configuration of the X-31 since its initial flights. In particular, the original pitot tube, which supplies airspeed information to the plane's flight control computers, had been replaced with another kind of pitot tube known as a keel probe. The keel probe gave more accurate airspeed data at high angles of attack, but it was more vulnerable to icing, especially since the keel probe on the X-31 did not have any pitot heat.
We were never to fly the airplane in ice. That was a prohibited maneuver. So if you're prohibited from flying in ice, you don't need a heater.
Normally, the conditions at Edwards are warm and dry enough that icing, or pitot heat, isn't a concern. But January 19, 1995 was not a normal day.
The unusual part of the day was we had a high humidity at altitude, actually conducive for freezing conditions. And airplane was operated for in and out of some fairly high moisture content for extended periods of time. Led to some indications in the cockpit and the control room that it was causing problems with the air data system.
This particular airplane had a limit to not fly through clouds, through visible moisture. That day, we were flying very close to and occasionally in and out of very thin cirrus cloud. It didn't particularly worry me because everything seemed to be going along quite normally.
But some minutes, like 5, before the airplane went out of control and the pilot jumped out, the pilot observed that there was some moisture around where he was. So he turned the pitot heat switch on. Now, clearly when he turned the pitot heat switch on, he expected that the pitot heat would be working. About 2.5 minutes later, which is 2.5 minutes before the accident, he mentioned that fact to the control room.
Okay, remind me I just put the pitot heat on. Remind me to put it off. Copy that. We ready? The pitot heat's not hooked up on a keel probe. Copy that. You ready?
Mysteriously, to this day, the control room gave him no response. They had an internal discussion as the clock clicked down, and internally it was commented that the pitot heat was not hooked up.
But this vital piece of information was not relayed to the pilot for more than 2 minutes, and even when it was, the information was not stated as clearly or strongly as it could have been.
And pitot heat. Well, leave it on for a moment. Yeah, we think it may not be hooked up. It may not be hooked up, that's good. I like this.
We had side discussions that should have been going on the intercom so that everybody in the control room was part of the conversation. Instead, we'd pulled our headsets aside so that we could talk to each other because we're sitting adjacent to each other. And that's another part of just control room discipline that we broke down on.
Meanwhile, the first signs of trouble were beginning to appear. So now,
the pilot sees an anomaly in his airspeed. He's at 20 degrees angle of attack, and he can see that. And he says to the ground, and I briefed this many times, he said, "I'm at 277, I mean 207 knots.
And the airspeed is off, reading 277 knots at 20 AOAs. Okay, pitch up this.
Well, anybody that's been on the program, and lots of people have been on many years, would know that 20 degrees angle of attack is somewhere around 135 knots, 140 knots, doesn't matter. It's not 207 knots.
Apparently, no one in the control room caught the possible significance of that discrepancy. And perhaps even more importantly, neither did the chase pilot, for the simple reason that he couldn't hear any of the pilot's transmissions.
We had a mechanism of hot mic, very important to the pilot in the X-31, that he'd be able to talk to the control room without having to press buttons at certain key times, especially at high angle of attack, which was not going to be a factor in this flight because it was going to go to about 20 degrees angle of attack. But it was a general operating procedure that was compounded because our hot mic system didn't work always very well. And when it didn't work, it put a lot of static in the earphones of the chase pilot who wanted to hear the hot mic to know what's going on.
So it was the one-sided nature of the communication that kept me from having the situational awareness to be able to step in and say, hey, I'm reading X knots and you guys are reading Y knots, and these two numbers should be the same, and they're not.
The X-31 did indeed have an air data problem. The unheated keel probe had frozen over in the cool, moist conditions, causing it to start giving incorrect airspeed information to the X-31's flight control computers.
In terms of the accepted risk, the failure of the pitot-static system or damage to it was well known. It was well understood. The pilot himself had simulated the failure in simulations before we even got the airplane. And it probably helped him understand that he had to get out of the airplane because the time is short when the airplane is diverging.
And we went through quite a thorough review of the hazards that we knew or could come up with based upon the design of the flight control system. And we thought we had a good handle on that. We thought we could lose the whole nose boom. We could take a bird strike, wipe out the whole nose boom, and fly home safe. As a result of that, we thought we had a pretty robust system.
The reason the team thought they had a robust system was the X-31's flight control system was designed with 3 backup reversionary modes the pilot could select in the event of an air data problem or other systems failures.
So in the case of if you saw something that was not right, or the control room saw something that was not right with respect to the airspeed system, they could tell the pilot to go to R3.
R3 was a reversionary mode that would have removed within 2 seconds the airspeed data inputs into the flight control system. The control surface response to pilot inputs would then be independent of airspeed, allowing the airplane to remain controllable for the remainder of the flight back to the landing.
The accepted risk was probably reasonable, but here's the kicker. The consequences of a failure are so high here that you really needed to put some special attention on this. The designer did by putting R3 in.
But nobody on the test team, including the pilot, realized that the X-31 was experiencing an air data problem that would require implementing the R3 reversionary system.
For several minutes, we had indications that the airspeed was becoming poor, both in the cockpit and the control room. In our last-ditch catch, nobody stood up and yelled, "Wait a minute, this can't be right."
Because had we realized what was going on, the control system had the ability to go to fixed flight control gains, and with fixed flight control gains, it would not have been a problem. They would have been able to land the airplane safely. But we just never got enough information to make the decision to do that.
We had an alternate airspeed indicator that used a different pitot tube, which would be less susceptible to icing than this special tube. It was at the pilot's right-hand knee, and he never looked at it. We had a lack of attention to the reversionary modes. Gradually, we were not thinking. We learned to depend on the control room. They're going to tell us when we need to go to R2 or R1 or R3. We need to know as pilots, which we kind of forgot, where are the safety nets? The safety nets, push the right button, didn't get the test data, but you bring the aircraft back. So if you didn't understand what was happening, we should have been constantly reminded, push the button and talk about it.
Pilot obviously wasn't concerned. His experience, probably, if you look at the control room, the pilot and everybody involved in that day's activity, he was the most experienced X-31 in that day's activity. He had been on a program since Palmdale. So he noticed something, but he wasn't concerned. So, and he didn't ask for help that I was aware of. And so I think the control room said, well, he's not that panicked, I'm not that panicked. And I think that fed off each other a little bit.
The team moved on to the final test point of the day, a simple automatic control response test that required only a command from the pilot to initiate. But once again, the airplane did not respond as expected.
He hits the box, presses the button, and he says, I don't get anything. Well, he didn't get anything because the box was designed not to put any input if you went beyond a certain speed, like 200 knots. So it was seeing the false airspeed of 200 plus knots. And when he pushed the button, it didn't work.
3, 2, 1, go.
What? Doesn't do anything.
But it didn't work because something was wrong. And the control room came back and finally just kind of ignored that and said, it's all okay, you know, RTB now.
It's almost like expecting to hear that went fine. You know, after this program with hundreds of flights and everything going perfectly, in your mind, you're hearing things that weren't happening. Everything's fine, worked fine, let's come home.
The normal operation of the system was expected that the system would identify the problems itself, that it would not be the people on the ground identifying an air data problem and calling for fixed gains. Although it was certainly capable of putting that, the expectation would be that the system would do its own self-diagnosis and identify failures.
But the failure we had was a slow failure of the tube, slowly building the ice up. So the changes in the speed were within perfectly reasonable numbers for a real airplane. Software is just not capable of detecting that failure for that system.
There was one or two people that actually knew that there was these little tiny areas that, yeah, it couldn't handle it, but that word never got out. They never stood up and said, boss, that's not quite right. You know, you can handle it over 95 or 99% of the area, but there's really a couple little areas the automated system can't handle it. And that didn't come out till after the accident. I never did get to talk to them about it, but I just kind of felt they didn't want to stop the program, thought it was of no real issue because of the difficulty of getting to such a small area of the envelope.
But as the X-31 began to descend on its return to base, the problems caused by the failure of its air data system became far more pronounced.
We have frozen the pitot tube now, and it's stuck. It's got what it had in it, and it's going to hold that pressure. Now when you start down with a frozen pitot tube, the airspeed, what you see, the false airspeed that he saw, will decrease as he decreases altitude. But we are seeing, the control room is seeing, they have a big display, this big. The pilot is seeing every time he turns his head, he's seeing the airspeed in the HUD. And now it's perhaps at one point, it's at 150 knots. It cannot be at 150 knots. And then it's at 100 knots. And it cannot be at 100 knots. And going on down, it finally, right just before the accident, it gets to, 48 knots, which is the minimum it's going to read. But the control system in the airplane is getting this wrong information. And this is a complex closed-loop system, and when you put too much gain in, it will start to get unstable, and it will start moving the controls, which it did a matter of seconds. And finally, it dramatically pitches up. The pilot, of course, tries to prevent that, and I'm sure the instant that he hit the forward stop and realized he was out of control, he did the natural thing, was eject from the airplane.
We were RTB, return to base, and I started to rejoin on the X-31. As I came up on his right side, about 100 yards away and closing, I saw the airplane start to go into a small wing rock that progressively got larger and larger. And as I got within about 200 feet of him, the airplane pitched up vertical. And approximately the time that I passed to beam him, I saw the pilot eject.
Okay, Natural One, we have an ejection. We have an ejection. Natural One, do you read?
Yeah, we copy, Dana, we copy.
And report as G584 has ejected the aircraft is descending over the North Base area. I have a chute. Report, that's 850. How do you read? 850. Yes, sir. That 584 has ejected from his aircraft. The aircraft is descending north of North Base. The pilot is in the chute at this time, descending approximately 1 mile north of North Base.
So there was the knowledge and training in the simulation that taught the pilot that when he started seeing the airplane was oscillating, was not controlled, he knew that he had to get out of the airplane very fast or else the airplane would go into a tumble. And he did do that, and that saved his life. I also know that the pilot, as he was ejecting from the airplane, had thoughts of maybe I should have tried a reversionary mode. But at that point, if he would have hesitated any longer, he would have been probably lost with the airplanes.
I did not connect until after the plane departed. And while the plane was tumbling, I made the connection. Pitot system had to be frozen. And just didn't come to the realization soon enough to do anything about it in the control room.
Less than 4 minutes after the first comment about pitot heat was recorded between the pilot and the control room, the X-31 crashed just north of Edwards Air Force Base. How could such a routine operation have ended in disaster when flights with far higher risk had been completed safely? And more importantly, what can we learn from the answers to that question?
Every person involved in an experimental flight research program should actually study the mishaps of all experimental aircraft in the past 20 to 30 years. There's a lot of things you can learn because human nature doesn't change, the processes don't change. It's always the same set of contributing factors, just the names and the details change. Of the 10 things, for example, that I describe as contributing causes of the mishap, 6 of them occurred prior to the day of flight. 4 occurred within about 2 minutes. So we had a better chance of working on the 6 than we did on the 4.
In some senses, the X-31 accident started 6 years earlier when the plane was first developed and tested at Rockwell.
We had a hazard analysis from the initial design, and in the accident that had to actually get dusted off. You should never have to dust off one of those. Everybody familiar with the program, at all those levels need to have a really good, comfortable feeling of what those hazards are and what is accepted in the risk. There was a redo of that analysis as we moved to NASA in '92, and I think it was clear after the accident, not everybody really understood what that design was to the detail you needed to understand the full risk of the program. Clearly, from 1990 to 95, you have a large team turnover. We changed locations. We expanded the objectives of the program. And as time rolls on and the new people come in, not everybody has the same understanding or appreciation of the kind of vehicle we're operating. It's a special airplane. It's not the same risk as any other airplane. And to operate it every day, you really ought to have the same appreciation for the risk. And I don't think we as a team did a good job of keeping everybody that came to the program with the same level of understanding of both the design and the risk on the airplane. We shouldn't have had a control room, a pilot, and a team that day that didn't understand that fundamental fact. And it's not elaborate, it's just straightforward. The airspeed I see in the HUD is the airspeed the computer uses. If the airspeed I see has got a problem, the airplane's got a problem. And that fact, it didn't get communicated correctly from old team members to the new team members. And if it had, I don't think there'd have been anybody in that room that wouldn't have yelled stop and jumped off the bridge to make it happen.
There were errors made. The pitot heat circuit breaker was disabled, but there was no placard in the cockpit to say no pitot heat. And notices of the configuration were sent around, but here also we probably lacked one step, and that is to know that everybody got the message. It's one thing to send it out, it's another thing to verify everyone has read and understood it. And so that procedure was changed, by the way, so that people ripped off the bottom of the page and sent it back. I've seen it.
Ironically, the X-31 program also may have been a victim of its own success.
I never saw complacency in this team. I went to tech briefs, crew briefs. It was treated very professionally, and in fact, to some extent, it was treated like an experimental airplane every flight. But certainly you have to think that after hundreds of flights, excellent results, and the fact that none of these hazards, these terrible things that you predict could happen, has ever happened, it could lead you to be less sensitive to things that are happening. Maybe just a little bit of the edge comes off.
Those single point failures were identified, and we made some actual changes to the design of the airplane to account for that. And again, that was in 1989. Why all those were there and what the concerns were and how to mitigate them and how to worry about them became We hadn't had any problems with that for 5 years. And I think, again, the complacency just got built into the team. It worked fine. We never had a problem. And those little hairs on the back of your neck weren't geared to stand up when people started having airspeed problems.
Our control rooms used to have a saying on them to prepare for the unexpected and expect to be unprepared. And I think that's a truth in the flight test business, that that we need to keep that in mind continuously. I wish that sign was still up there, because that reminder needs to be enforced all the time.
Well, certainly in the case of the X-31, we were returning to base after 2 exhausting days, 7 flights. Ship 1 was now going into the boneyard, or at least it was being retired from the test program. And so we're finally finished. Is everybody paying attention like they should be? Obviously not.
And while the X-31 program flights were highly successful, they did not include an element that might have helped prime the program team to take the one mitigating action that could have brought the X-31 home safely.
We've debated amongst ourselves whether we actually would have been able to convince anybody to use the fixed gain system, because there was not an obvious need for it. The pilot may have been better prepared when things started to go awry to select fixed gains, but I don't know if we ever really would have done it in that situation, because we didn't have a real problem. We did have a real problem, but it hadn't been diagnosed as a real problem.
On the previous program, the X-29 program, we had the same sort of thing. We had an analog reversion mode, a digital reversion mode, and the normal mode of the airplane. We routinely at every test point selected those backup modes, flew them around, so the pilots were much more familiar and much more comfortable with selecting those modes. On the X-31 program, we never selected those modes intentionally. We only used them when we had a sensor failure or the system told us to select those modes.
On the day of the mishap itself, there were additional links added to the chain. There were unusual weather conditions that created an uncommon and unexpected kind of flight hazard, and the team was working with a flawed hot mic system that kept the chase pilot from hearing critical communications from the X-31 pilot.
So, some links in the chain are already built there. Management links, control room has now talked internally, they've heard some things, they haven't said anything. Some more links are built. We got this chain is building now. The chase pilot didn't hear anything about this, didn't know that he didn't know anything was wrong with the airplane until he saw the airplane pitch up and the pilot jump out. Whereas he could have stopped this anytime.
At any rate, it's a total team concept, and the chase pilot has to be part of that team. The team has to have total communication. So the use of a hot microphone frequency that did not allow the chase pilot to stay up with what was going on with the airplane was essentially keeping me from doing my job, at least at a certain level. And that's one of the things that we changed in the way we do business here at Dryden, is to allow the chase pilots either access to the hot mic or to ensure that all critical communications are transmitted so that all the players are kept up to speed with what's going on. And that was a direct fallout of how the X-31 operation was handled that day.
If one or more of these contributing factors had been caught and addressed prior to January 19th, the chain of events leading up to the accident might have been broken before the flight even took place. Yet there were still opportunities to avoid the mishap, even in the last few minutes of the X-31's flight. So why didn't the team manage to recognize, communicate, and respond to the X-31's pattern of anomalies in time?
So we were seeing inconsistencies between the data from the aircraft system and what we knew of the physics of the problem, that it could not be. That you could not have that airspeed and that angle of attack simultaneously. And for me, I just remember thinking, gosh, I can't wait till we get the data from this flight, because I want to see what's going on. I knew there was an anomaly. We had talked about it between the engineers. We didn't talk about it on the intercom, though. It was sidebar conversations in the control room.
Well, many of us are engineers, and we see an issue. Oh, this is interesting. I wonder what's causing that. And you start thinking about it and trying to figure out what is the answer. In the meantime, the seconds are clicking by. And really the right response is, something's going on I don't understand. Let's call a halt here and let's just figure it out.
We should have, at the first call of an airspeed failure, puckered up. Whether you're RTB at that point or not, it wouldn't have changed. The kind of failure that was occurring should have triggered a lot of emotion anywhere in the flight envelope.
In the case of any discrepancy, anything that doesn't sound right, feel right, smell right, let's stop and think it over. And I think that kind of attitude has been built in now into the control room, mission control room processes since then.
We were flying lots of flights. At the peak of the program, there would be days when there would be 5 flight days. I think on that particular day, we were only doing 3 flights. And it was the last flight of the day. It was the last flight for the first airplane. And we had completed all the test points for that mission. In addition, we were going through the RTB, or return to base checklist. And at that point, every one of us kind of relaxed. Like I said, what was going through my mind is, I can't wait to get this data. Something funny is going on, and I want to figure it out. And that's another lesson learned, that when we talk about it all the time, the mission's not over till the airplane's on the ground and the engine's shut down. And you see it a lot in the control rooms. We start getting ready to land, and everybody relaxes a little bit. And that's a lesson I've carried with me, is you need to continue the vigilance there in the flight.
Communication is what it's all about. So everybody, we have to have the communication links. We didn't have it to the chase. Hot mic was a contributing factor. We didn't have it in the control room. We discussed things internally, was not transmitted to the pilot. We have to have an environment and built where people can speak up when they think something's wrong. They don't have to be right. If they're concerned, they should be able to speak their mind, put their hand up, and we stop the train. And then we say, no, you weren't right, it's okay. Fine, we go on. We didn't do that. We never stopped the train.
We had a problem, and we didn't stop, not only testing, we didn't stop flying and come home. But you can't stop for every problem. I mean, that's unrealistic. You have problems in flight. The combination that went with that is we didn't understand the severity of the problem. So you have to understand your vehicle and the consequences of failures. And if one of those failures has a serious consequence, you need to stop and come home.
Clearly, there are lessons to be learned in the entire progression of events that led up to the X-31 mishap. And yet, the X-31 program did not end with that crash. The next chapter of its story is an equally important reminder of why flight test remains such a valuable step in proving a concept or technology, despite the hazards that come with the territory. The X-31 had been scheduled to fly at the Paris Air Show in June of 1995. But after the loss of one of the 2 X-31 ships less than 6 months before the show, it seemed an impossible goal.
Having lost the airplane, pretty much everyone thought that's it. Because flying the kind of maneuvers that this airplane can do at 500 feet sounded a lot riskier to me after you lose an airplane. The team really talked a lot about this and decided that it did not want to end this program on a low note. And so we made the decision to press on with the Paris Air Show.
A huge thing to sign up for was to take an airplane that just crashed and to turn it around to go do a low altitude, high angle attack flight demonstration. That took a lot of guts on everybody's part and a lot of good engineering work to make that happen.
We actually flew the X-31 84 days after the mishap. This required the board to reach its conclusions, to write a report, for the team to react to all of the issues and problems and contributing factors brought up, solve the problem, and get it into an airplane and get it qualified for first flight. It was all done in 84 days. It does tell you about the quality of the team.
Right. A totally different airplane, which will demonstrate a most remarkable flying ability. It is the X-31 technology demonstrator.
after the mishap, I think the program made a spectacular recovery and made one of the finest appearances ever at the Paris Air Show. The airplane did things that no other airplane could do. The Russians had demonstrated post-stall maneuvers with the Cobra, but it was really an open-loop maneuver. They pulled back on the stick and then you flew out of it at the end. Whereas the X-31 just demonstrated the ability to control all axes of the airplane, pitch, roll, and yaw simultaneously while operating at the extremes of the flight envelope.
So, fantastic air show, absolutely the most spectacular I've ever seen, and I saw every one of them. And I stood with the crowd on some of them, and I was in the control tower on others, and out right underneath it at other times. But to be with the crowd and watch, even hardened veterans, military, had no concept of what it could really do, and seeing it was jaw-dropping for the crowd. It was spectacular.
The announcement that the X-31 was next to fly, as you look down the row of chalets, you see all the people coming out of the chalets, out against the railing to watch the flight.
If the events leading up to the X-31's mishap are a reminder of how much vigilance is required in order to mitigate the risks inherent in a flight test program, the X-31's Paris Air Show performance was a reminder of why those risks are still worth undertaking.
Flight test of all kinds is inherently dangerous. There are risks involved in it. Never can you or anybody else bring it to zero. Well, you can. That's keep the airplane in the hangar. Don't fly. Well, if you don't fly, you don't move forward, you don't discover, you don't prove things. So you need to take some risks, but you need to do it in a controlled fashion.
The reason we spend time on looking at these accidents is that there aren't many accidents. We don't lose many airplanes in flight research activities at Dryden. We haven't over the years. And so when you do have one, you better learn everything about it. In fact, you should do the same thing for close calls.
The lessons to be learned. Don't assume that they've been learned. We can always, at every new group, will have to learn the same lessons, and you don't want to do it the hard way with an accident. Safety is everybody's business. Flight test safety is everybody's business on the team, and there are no processes. You have to have processes, but there are no perfect processes that will not require good judgment from all levels of the program.
If you're a program that's been operating for a long time, potentially, you've got a lot of turnover, you're in your mature years, all your documentation is years old, maybe you better make sure that all your new people are as good as your old people, that you've reviewed your documentation and it's still correct and you all understand it, and that what you're doing today still makes sense from how you started. So maybe one of those, if you're in that area, you ought to take a look at yourself.
It always is clear what you should do after the fact, or should have done rather, and nobody thinks it's ever going to happen to them. To lose judgment, to lose this communication link, to not do the right things.
So what is the message? What is the message for the team? It may mean that I am a part of the chain, and that if I don't catch this, and if other people don't catch their mistakes, we will run through the entire chain and lead to a mishap. So it means that every individual in the program from beginning to end, no matter what the job is, from the highest level job to the lowest level job in terms of detail, they have to take it very seriously. And that's a message that you have to keep promoting, pronouncing, and explaining. It sounds trite, but everybody is responsible for safety. If you think some safety office analysis is going to find the things, they won't. Mishaps can occur everywhere, but the point is you have to fly safely, but fly.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.